Hello and welcome to video number 7 or stream number 7, I must say, of the Learn Along series. We are currently studying NLP with deep learning from Stanford. This is course CS224N. We are watching videos of the winter 2019 session. Yesterday we did lecture number 5, which was around dependency parsing. It's basically more on linguistics, or the approach of how do we understand and parse what are all of the dependencies in a statement, trying to attach the phrase of a noun to the adjective, to the adverb, verb, and preposition and all sort of things, and also get to know how complex English as a language is. So we did that, and then I think today we are getting into language models and recurrent neural networks. Super excited about today's session because I think this becomes a good base builder, RNNs, for what's coming in the future. So without further ado, let me quickly do a sound check, because in the past I've been told we've had issues, so I'll be back in 1 minute. Okay, I think we're all fine. Let's jump right into this. I'll open up the link. This is not opening for some reason. Okay, here we go.
Hi everyone, I'm Abby. I'm the head TA for this class, and I'm also a PhD student in the Stanford NLP group. And today I'm going to be telling you about language models and recurrent neural networks.
Sorry, this is a little laggy, so I'm waiting on this to get loaded properly.
So here's an overview of what we're going to do today.
Okay.
Hi everyone, I'm Abby. I'm the head TA for this class, and I'm also a PhD student in the Stanford NLP group. And today I'm going to be telling you about language models and recurrent neural networks. So here's an overview of what we're going to do today. Today, first we're going to introduce a new NLP task, that's language modeling. And that's going to motivate us to learn about a new family of neural networks, that is recurrent neural networks, or RNNs. So I'd say that these are two of the most important ideas that you're going to learn for the rest of the course. So we're going to be covering some fairly core material today. So let's start off with language modeling. Language modeling is the task of predicting what word comes next. So given this piece of text, the students opened their blank. Could anyone shout out a word which you think might be coming next? Book. Mind. What else? I didn't quite hear them, but yeah, these are all likely things, right? So these are some things which I thought students might be opening. Students open their books, seems likely. Students open their laptops. Students open their exams. Students open their minds. Incredibly, someone came up with that one just now. It's kind of a metaphorical meaning of opening. So you are all performing language modeling right now. In thinking about what word comes next, you are being a language model. So here's a more formal definition of what a language model is. Given a sequence of words, x1 up to xt, a language model is something that computes the probability distribution of the next word, xt plus 1. So a language model comes up with the probability distribution, the conditional probability of what xt plus 1 is given the words so far. And here we're assuming that xt plus 1 can be any word W from a fixed vocabulary V. So we are assuming that there's a predefined list of words that we're considering. In this way, you can view language modeling as a type of classification task, because there's a predefined number of possibilities. And we call a system that does this a language model. There's an alternative way of thinking about a language model as well. You can think of a language model as a system which assigns probability to a piece of text. So for example, if we have some piece of text x1 up to x capital T, then the probability of this text according to the language model can be broken down. So just by definition, you can say that the probability is equal to the product of all of these conditional probabilities. And the form inside the product is exactly what our language model provides. So you can think of these things as somewhat equivalent. Predicting the next word gives you a system that can give the probability of a given piece of text. So in fact, you use language models every day. For example, when you're texting on your phone and you're writing a message, then most likely if you have a smartphone, it will be predicting what word you might be about to say. So if you say, I'll meet you at the, your phone might suggest perhaps you mean airport or cafe or office, for example. Another situation in which you use language models every day is when you search for something on the internet, for example, Google, and you start typing your query, then Google tries to complete your query for you. And that's language modeling. It's predicting what word or words might come next. So that's what a language model is. And the question is, how would you learn a language model? So if I was to answer that question in the pre-deep learning era, which was really only a few years ago, the answer would be you would learn an n-gram language model. So today, first, we're going to learn about n-gram language models. So before I can tell you what an n-gram language model is, you need to know what an n-gram is. So by definition, an n-gram is a chunk of n consecutive words. So for example, a 1-gram or unigram is just all of the individual words. In this sequence, it would be the students opened there. A 2-gram or bigram would be all of the consecutive chunks of pairs of words. The students opened there, and so on for trigrams and 4-grams, etc. So the core idea of an n-gram language model is that in order to predict what word comes next, you're going to collect a bunch of statistics about how frequent different n-grams are from some kind of training data, and then you can use those statistics to predict what next words might be likely. Here's some more detail. So to make an n-gram language model, first you need to make a simplifying assumption, and this is your assumption. You say that the next word, xt plus 1, depends only on the preceding n minus 1 words. So what we're assuming is that the probability distribution, the conditional probability of xt plus 1, given all of the words so far, we're just going to simplify that and say it only depends on the last n minus 1 words, and that's our assumption. So by the definition of conditional probability, we can say that this probability is just the ratio of two different probabilities. So on the top, you've got the probability of a particular n-gram, and on the bottom, we've got the probability of a particular n minus 1 gram. This is a little hard to read because of all the superscripts, but I'm going to give an example with words on the next slide. OK, so that's the definition of the probability of the next word. But the question remains, how do we get all of these n-gram and n minus 1 gram probabilities? So the answer is we're going to get them by counting them in some large corpus of text. So we're going to approximate these probabilities just by the count of the number of times that these particular n-grams and n minus 1 grams appeared in our training corpus. OK, so here's an example with some words. Suppose we're trying to learn a 4-gram language model. And suppose that we have a piece of text that says, as the proctor started the clock, the students opened their blank. And we're trying to predict what word is coming next. So because we're learning a 4-gram language model, our simplifying assumption is that the next word depends only on the last 3 words, the last n minus 1 words. So we're going to discard all of the context so far, except for the last 3 words, which is students opened there. So as a reminder, our n-gram language model says that the probability of the next word being some particular word W in the vocabulary is equal to the number of times we saw students open their W divided by the number of times we saw students open there in the training corpus. So let's suppose that in our training corpus, we saw the phrase students opened there 1,000 times. And suppose that we saw students open their books 400 times. This means that the probability of the next word being books is 0.4. And similarly, let's suppose that we saw students open their exams 100 times. This means that the probability of exams given students open there is 0.1. Is there a question?
What does it matter?
The question question is, does the order of the words matter? And the answer is yes, the order of students opened there does matter. It's different to their students opened. So the question I want to raise now is, was it a good idea for us to discard the proctor context? If you look at the actual example that we had, the example was, as the proctor started the clock, the students opened their blank. So do we think that books or exams is more likely given the actual context, the full context? Yep. Exams, right. Exams is more likely because the proctor and the clock heavily implies that it's exam scenarios. They're more likely to be opening the exams than the books, unless it's an open book exam. But I think overall it should be exams. So the problem that we're seeing here is that in the training corpus, the fact that students were opening something means that it's more likely to be books than exams because overall books are more common than exams. But if we know that the context is the proctor and the clock, then it should be exams. So what I'm highlighting here is a problem with our simplifying assumption. If we throw away too much context, then we are not as good as predicting the words as we would be if we kept the context. Okay, so that's one problem with n-gram language models. There are some other problems as well. So here again is the equation that you saw before. One problem, which we're going to call the sparsity problem, is what happens if the number on top, the numerator, what if that count is equal to 0? So what if for some particular word W, the phrase students open their W never occurred in the data? So for example, let's suppose students open their Petri dishes is fairly uncommon and it never appeared in the data. Then that means that our probability of the next word being Petri dishes will be 0. And this is bad because it might be uncommon, but it is a valid scenario, right? If you're a biology student, for example. So this is a problem, and we call it the sparsity problem, because the problem is that if we'd never seen an event happen in the training data, then our model assigns 0 probability to that event. So one partial solution to this problem is that maybe we should add a small delta, a small number delta, to the count for every word in the vocabulary. And then this way, every possible word that could come next has at least some small probability. So Petri dishes will have some small probability, but then so will all of the other words, which are possibly bad choices. So this technique is called smoothing, because the idea is that you're going from a very sparse probability distribution, which is 0 almost everywhere, with a few spikes where there's been n-grams that we've seen. It goes from that to being a more smooth probability distribution, where everything has at least a small probability on it. So the second sparsity problem, which is possibly worse than the first one, is what happens if the number in the denominator is 0? So in our example, that would mean, what if we never even saw the trigram students opened there in the training data? If that happened, then we can't even calculate this probability distribution at all for any word W, because we never even saw this context before. So a possible solution for this is that if you can't find students opened there in the corpus, then you should back off to just conditioning on the last 2 words rather than the last 3 words. So now you would be looking at times when you'd seen opened there and seeing what words come next. So this is called back off because in this failure case for when you have no data for your 4-gram language model, you're backing off to a trigram language model. A possible solution for this. Are there any questions at this point? If you can't find students opened there. Okay. So another thing to note is that these sparsity problems get worse if you increase n. If you make n larger in your n-gram language model, and you might want to do this. For example, you might think, I want to have a larger context so that I can pay attention to words that happened longer ago, and that's going to make it a better predictor. So you might think making n bigger is a good idea. But the problem is that if you do that, then these sparsity problems get worse. Because let's suppose you say, I want a 10-gram language model. Then the problem is that you're going to be counting how often you've seen certain 9 grams and 10 grams. But 9 grams and 10 grams, there's so many of them that the one you're interested in probably never occurred in your training data, which means that the whole thing becomes dysfunctional. So in practice, we usually can't have n much bigger than 5. Okay, so that was 2 sparsity problems with n-gram language models. Here's a problem with storage. So if we look at this equation, you have to think about what do you need to store in order to use your n-gram language model. You need to store this count number for all of the n-grams that you observed in the corpus when you were going through the training corpus, counting them. And the problem is that as you increase n, then this number of n-grams that you have to store and count increases. So another problem with increasing n is that the size of your model, of your n-gram model, gets bigger. Okay. So n-gram language models in practice, let's look at an example. You can actually build a simple trigram language model over a 1.7 million word corpus in a few seconds on your laptop. And in fact, the corpus that I used to do this was the same one that you met in assignment 1. It's Reuters corpus, which is business and financial news. So if you want to do this for yourself, you can follow that link at the bottom of the slide later. So this is something which I ran on my laptop in a few seconds. So I gave it the context of the bigram today, and then I asked the trigram language model what word is likely to come next. So the language model said that the top next most likely words are company, bank, price, Italian, Emirate, etc. So already just looking at these probabilities that are assigned to these different words, you can see that there's a sparsity problem. For example, the top 2 most likely words have the exact same probability. And the reason for that is that this number is 4 over 26. So these are all quite small integers, meaning that we only saw today the company and today the bank 4 times each. So this is an example of the sparsity problem because overall these are quite low counts. We haven't seen that many different versions of this event, so we don't have a very granular probability distribution. But in any case, ignoring the sparsity problem, I would say that overall these top suggestions look pretty reasonable. So you can actually use a language model to generate text, and this is how you would do it. So let's suppose you have your first 2 words already. You condition on this and you ask your language model what's likely to come next. So then given this probability distribution over the words, you can sample from it. That is, select some word with the associated probability. So let's suppose that gives us the word price. So then price is your next word, and then you just condition on the last 2 words, which in this example is now the price. So now you get a new probability distribution, and you can continue this process, sampling, and then conditioning again and sampling. So if you do this for long enough, you will get a piece of text. So this is the actual text that I got when I ran this generation process with this trigram language model. So it says, today the price of gold per ton, while production of shoe lasts and shoe industry, the bank intervened just after it considered and rejected an IMF demand to rebuild depleted European stocks, September 30th, end primary 76 counts a share. Okay, so what do we think about this text? Do we think it's good? Are we surprised? I would say that in some ways it is good. It's kind of surprisingly grammatical. It mostly kind of pauses. But you would definitely say that it doesn't really make any sense. It's pretty incoherent. And we shouldn't be surprised that it's incoherent, I think, because if you remember, this is a trigram language model. It has a memory of just the last, 3 or 2 words, depending on how you look at it. So clearly, we need to consider more than 3 words at a time if we want to model language well. But as we already know, increasing n makes the sparsity problem worse for n-gram language models, and it also increases the model size. Was that a question?
How does it know when to put commas?
So the question is, how does the n-gram language model know when to put commas? So you can decide that commas and other punctuation are just another kind of word, as it were, or token. And then to the language model, it doesn't really make much difference. It just views that as another possible word that can be predicted. That's why we've got the weird spacing around the commas. It's because it was essentially viewed as a separate word. Okay. So this class is called NLP with deep learning. So you're probably thinking, how do we build a neural language model? So let's just recap in case you forgot. Remember that a language model is something that takes input, which is a sequence of words x1 up to xt, and then it outputs a probability distribution of what the next word might be, xt plus 1. Okay, so when we think about what kind of neural models have we met in this class so far, we've already met window-based neural models. And in lecture 3, we saw how you could apply a window-based neural model to named entity recognition. So in that scenario, you take some kind of window around the word that you care about, which in this example is Paris, and then you get the word embeddings for those, concatenate them, put them through some layers, and then you get your decision, which is that Paris is a location, not a person or an organization. So that's a recap of what we saw in lecture 3. How would we apply a model like this to language modeling? So here's how you would do it. Here's an example of a fixed window neural language model. So again, we have some kind of context, which is as the proctor started the clock, the student's open there, and we're trying to guess what word might come next. So we have to make a similar simplifying assumption to before. Because it's a fixed size window, we have to discard the context except for the window that we're conditioning on. So let's suppose that our fixed window is of size 4. So what we'll do is similarly to the NER model, we're going to represent these words with one-hot vectors, and then we'll use those to look up the word embeddings for these words using the embedding lookup matrix. So then we get all of our word embeddings E1, 2, 3, 4, and then we concatenate them together to get E. We put this through a linear layer and a nonlinearity function f to get some kind of hidden layer. And then we put this through another linear layer and a softmax function, and now we have an output probability distribution y hat. And in our case, because we're trying to predict what word comes next, our vector y hat will be of length v, where v is the vocabulary, and it will contain the probabilities of all the different words in the vocabulary. So here I've represented that as a bar chart, where if you suppose you've got all of the words listed alphabetically from A to Z, and then those are the different probabilities of the words. So if everything goes well, then this language model should tell us that some likely next words are books and laptops, for example. So none of this should be unfamiliar to you because you saw it all last week. We're just applying a window-based model to a different task, such as language modeling. Okay, so what are some good things about this model compared to n-gram language models? So one advantage, I'd say, is that there's no sparsity problem. If you remember, an n-gram language model has a sparsity problem, which is that if you've never seen a particular n-gram in training, then you can't assign any probability to it. You don't have any data on it. Whereas at least here, you can take any, for example, 4-gram you want, and you can feed it into the neural net, and it will give you an output distribution of what it thinks the next word would be. It might not be a good prediction, but at least it will run. Another advantage is you don't need to store all of the observed n-grams that you ever saw. So this is an advantage. By comparison, you just have to store all of the word vectors for all the words in your vocabulary. But there are quite a lot of problems with this fixed window language model. So here are some remaining problems. One is that your fixed window is probably too small. No matter how big you make your fixed window, you're probably going to be losing some kind of useful context that you would want to use sometimes. And in fact, if you try to enlarge the window size, then you also have to enlarge the size of your your weight matrix W. So the width of W, because you're multiplying it by E, which is the concatenation of your word embeddings, the width of W grows as you increase the size of your window. So in conclusion, really, your window can never be large enough. Another problem with this model, which is more of a subtle point, is that x1 and x2, and really all of the words in the window, they're multiplied by completely different weights in W. So to demonstrate this, you could draw a picture. So the problem is that if you have your weight matrix W, and then you have your concatenation of embeddings E, and we have 4 embeddings, so we have E1, E2, E3, E4, and you multiply the concatenated embeddings by the weight matrix. So really, you can see that there are essentially kind of 4 sections of the weight matrix. And the first word embedding E1 is only ever multiplied by the weights that are in this section. And that's completely separate to the weights that multiply E2, and so forth. So the problem with this is that what you learn in the weight matrix in one section is not shared with the others. You're kind of learning a lot of similar functions 4 times. So the reason why we think this is a problem is because there should be a lot of commonalities in how you process the incoming word embeddings. So what you learn about how to process, the third embedding, some of it at least should be shared with all of the embeddings. So what I'm saying is it's kind of inefficient that we're learning all of these separate weights for these different words when there's a lot of commonalities between them. Is there a question?
Next time you draw something on the board, can you use a darker marker?
Darker marker, okay.
Read that from here.
Yeah, hopefully the verbal description is enough. Okay. So in conclusion, I'd say that the biggest problem that we've got with this fixed size neural model is that clearly we need some kind of neural architecture that can process any length input, because most of the problems here come from the fact that we had to make this simplifying assumption that there was a fixed window. Okay, so this motivates us to introduce this new family of neural architectures called recurrent neural networks, or RNNs. So this is a simplified diagram that shows you the most important features of an RNN. So we have, again, an input sequence of x1, x2, etc., but you can assume that this sequence is of any arbitrary length you like. The idea is that you have a sequence of hidden states. Instead of just having, for example, one hidden state, as we did in the previous model, we have a sequence of hidden states, and we have as many of them as we have inputs. And the important thing is that each hidden state, ht, is computed based on the previous hidden state and also the input on that step. So the reason why they're called hidden states is because you could think of this as a single state that's mutating over time. It's kind of like several versions of the same thing. And for this reason, we often call these time steps, right? So these steps that go left to right, we often call them time steps. So the really important thing is that the same weight matrix W is applied on every time step of this RNN. That's what makes us able to process any length input we want, is because we don't have to have different weights on every step, because we just apply the exact same transformation on every step. So additionally, you can also have some outputs from the RNN. So these Y hats, these are the outputs on each step. And they're optional because you don't have to compute them, or you can compute them on just some steps and not others. It depends on what you want to use your RNN to do. Okay, so that's a simple diagram of an RNN. Here I'm going to give you a bit more detail. So here's how you would apply an RNN to do language modeling. So again, let's suppose that we have some kind of text so far. My text is only 4 words long, but you can assume that it could be any length, right? It's just short because we can't fit more on the slide. So you have some sequence of text which could be kind of long. And again, we're going to represent these via some kind of one-hot vectors and use those to look up the word embeddings from our embedding matrix. So then to compute the first hidden state, H1, we need to compute it based on the previous hidden state and the current input. We already have the current input, that's E1, but the question is, where do we get this first hidden state from, right? What comes before H1? So we often call the initial hidden state H0. We call it the initial hidden state, and it can either be something that you learn, like it's a parameter of the network and you learn how to initialize it, or you can assume something like maybe it's the 0 vector. So the formula we use to compute the new hidden state based on the previous one, and also the current input, is written on the left. So you do a linear transformation on the previous hidden state and on the current input, and then you add some kind of bias, and then put it through a nonlinearity, like, for example, the sigmoid function. And that gives you your new hidden state. OK, so once you've done that, then you can compute the next hidden state, and you can keep unrolling the network like this. And that's called unrolling because you're kind of computing each step given the previous one. All right, so finally, if you remember, we're trying to do language modeling. So we're trying to predict which word should come next after the student's opened there. So on this 4th step over here, we can use the current hidden state, H4, and put it through a linear layer and put it through a softmax function, and then we get our output distribution y-hat4, which is a distribution over the vocabulary. And again, hopefully we'll get some kind of sensible estimates for what the next word might be. Any questions at this point? Yep.
So the number of hidden states is always going to be the number of words in your input?
The question is the number of hidden states the number of words in your input? Yeah, in this setting here, yes. Or you could say more generally, the number of hidden states is the number of inputs. Yep.
And just as with the n-gram model, we could use the output as the input for the next mutation and text generation that way?
Yep, so the question is, as with the n-gram language model, could we use the output as the input on the next step? And the answer is yes, and I'll show you that in a minute. Any other questions? Yep.
Are you learning the embeddings?
The question is, are you learning the embeddings? That's a choice. You could have the embeddings be, for example, pre-trained embeddings that you download and you use those and they're frozen, or maybe you could download them, but then you could fine-tune them, that is, allow them to be changed as parameters of the network, or you could initialize them to, small random values and learn them from scratch. Any other questions? Yep.
So you said we use the same W matrix. When we do like back propagation, does that mean we only update like WE, or do we update both WH and WE?
So the question is, you say we reuse the matrix, do we update WE and WH or just one? So you certainly learn both WE and WH. I suppose I was emphasizing WH more, but yeah, they're both matrices that are applied repeatedly. There was also a question about backprop, but we're going to cover that later in this lecture. Okay, moving on for now. So what are some advantages and disadvantages of this RNN language model? So here are some advantages that we can see in comparison to the fixed window one. So an obvious advantage is that this RNN can process any length of input. Another advantage is that the computation for step T can, in theory, use information from many steps back. So in our motivating example, which was as the proctor started the clock, the students opened there, we think that proctor and maybe clock are both pretty important hints for what might be coming up next. So at least in theory, the hidden state at the end can have access to the information from the input from many steps ago. Another advantage is that the model size doesn't increase for longer input. So the size of the model is actually fixed. It's just WH and WE, and then also the biases, and also the embedding matrix, if you're counting that. And none of those get bigger if you want to apply it to more longer inputs, because you just apply the same weights repeatedly. And another advantage is that you have the same weights applied on every time step. So I said this thing before about how the fixed-sized window neural model, it was less efficient because it was applying different weights of the weight matrix to the different words in the window. And the advantage about this RNN is that it's applying the exact same transformation to each of the inputs. So this means that if it learns a good way to process one input, that is applied to every input in the sequence. So you could see it as more efficient in that way. Okay, so what are the disadvantages of this model? One is that recurrent computation is pretty slow. As you saw before, you have to compute the hidden state based on the previous hidden state. So this means that you can't compute all of the hidden states in parallel. You have to compute them in sequence. So especially if you're trying to compute an RNN over a pretty long sequence of inputs, this means that the RNN can be pretty slow to compute. Another disadvantage of RNNs is that it turns out, in practice, it's quite difficult to access information from many steps back. So even though I said we should be able to remember about the proctor and the clock and use that to predict exams, not books, it turns out that RNNs, at least the ones that I've presented in this lecture, are not as good as that as you would think. And we're going to learn more about both of these disadvantages later in the course, and we're going to learn something about how you can try to fix them. Have we got any questions at this point? Yep.
Why do you assume the WH are the same?
Sorry, can you speak up?
Why do you assume that the WH should be the same?
So the question is, why should you assume that the WH are the same? I suppose it's not exactly an assumption, it's more a deliberate decision in the design of an RNN. So an RNN is, by definition, a network where you apply the exact same weights on every step. So I suppose the question, why do you assume, maybe should be, why is that a good idea? So I've spoken a little bit about why it's a good idea, and this list of advantages, I suppose, are the reasons why you would want to do that. Does that answer your question?
Open their books, right? If you assume that WH are the same, you mean that like a Markov chain is like a Markov chain. You mean the transfer probability for the student who open their books that are the same, but actually they're not the same. The students open the four words, the transfer probability for the four words are not the same. So the underlayer probability for the WH shouldn't be the same. It's just an approximation, but it's not the best.
Okay.
I mean, if
so
you
I think
assume WH to be the same, it's good because you reduce your number of parameters. But this is just but this is just approximation. The underlying transfer probability shouldn't be the same.
Okay, so I think the question is saying that given that these words the students open there are all different and they're happening in different contexts, then why should we be applying the same transformation each time? So that's a good question. I think the idea is that you are learning a general function, not just how to deal with students, the one-word students in this one context. We're trying to learn a general function of how you should deal with a word given the word so far. You're trying to learn a general representation of language in context so far, which is indeed a very difficult problem. I think you also mentioned that something about an approximation. Another thing to note is that all of the hidden states are vectors, not just single numbers, right? They're vectors of length, 500 or something. So they have quite a large capacity to hold a lot of information about different things in all of their different positions. So I think the idea is that you can store a lot of different information in different contexts in different parts of the hidden state, but it is indeed an approximation and there is some kind of limit to how much information you can store. Okay, any other questions? Yep.
Since it can process any single length, right, what length do you use when you're training? And does the length you use for training affect WH?
Okay, so the question is, given that you can have any length input, what length is the input during training? So I suppose in practice, you choose how long the inputs are in training, either based on what your data is, or maybe based on your efficiency concerns. So maybe you make it artificially shorter by chopping it up. What was the other question?
Does WH depend on the length?
Okay, so the question was, does WH depend on the length used? So no, and that's one of the good things in the advantages list, is that the model size doesn't increase for longer input, because we just unroll the RNN, applying the same weights again and again for as long as we like. There's no need to have more weights just because you have a longer input. Yeah.
So how do we choose the dimension of the vector? Should it be the length of the number of words we have in
Okay.
the dictionary?
Are you asking about capital E or the lowercase e's?
Lowercase.
Okay, so the question is, how do we choose the dimension of the lowercase e's? So you could, for example, assume that those are just pre-trained word vectors like the ones that you used in assignment 1. Yeah, for example, Word2Vec, and you just download them and use them, or maybe you learn them from scratch, in which case you decide at the beginning of training how big you want those vectors to be. Okay, I'm going to move on for now. So we've learned what a RNN language model is, and we've learned how you would run one forward, but the question remains, how would you train an RNN language model? How would you learn it? So as always in machine learning, our answer starts with you're going to get a big corpus of text, and we're going to call that just a sequence of words, x1 up to x capital T. So you feed the sequence of words into the RNN language model, and then the idea is that you compute the output distribution y hat t for every step t. So I know that the picture I showed on the previous slide only showed us doing it on the last step, but the idea is that you would actually compute this on every step. So this means that you're actually predicting the probability of the next word on every step. Okay, so once you've done that, then you can define the loss function, and this should be familiar to you by now. This is the cross entropy between our predicted probability distribution y hat t and the true distribution, which is just yt, which is a one hot vector representing the true next word, which is xt plus 1. So as you've seen before, this cross entropy between those two vectors can be written also as a negative log probability. And then lastly, if you average this cross-entropy loss across every step, every t in the corpus times step t, then this gives you your overall loss for the entire training set. Okay, so just to make that even more clear with the picture, suppose that our corpus is the students open their exams, etc., and it goes on for a long time. Then what we'd be doing is we'd be running our RNN over this text, and then on every step we would be predicting the probability distribution y hats, and then from each of those you can calculate what your loss is, which is the jt. And then on the first step, the loss would be the negative log probability of the next word, which is, in this example, students, and so on. Each of those is the negative log probability of the next word. And then once you've computed all of those, you can add them all up and average them, and then this gives you your final loss. Okay, so there's a caveat here. Computing the loss and gradients across the entire corpus, all of those words x1 up to x capital T, is too expensive because your corpus is probably really big. So as a student asked earlier, in practice, what do you actually regard as your sequence? So in practice, you might regard your sequence as something like a sentence or a document, some shorter unit of text. So another thing you'll do is, if you remember, stochastic gradient descent allows you to compute gradients for small chunks of data rather than the whole corpus at a time. So in practice, if you're training a language model, what you're actually likely to be doing is computing the loss for a sentence, but that's actually a batch of sentences, and then you compute the gradients with respect to that batch of sentences, update your weights, and repeat. Any questions at this point? Okay. So moving on to backprop, don't worry, there won't be as much backprop as there was last week, but there is an interesting question here, right? So the characteristic thing about RNNs is that they apply the same weight matrix repeatedly. So the question is, what's the derivative of our loss function, let's say on step t, what's the derivative of that loss with respect to the repeated weight matrix, WH? So the answer is that the derivative of the loss, the gradient with respect to the repeated weight, is the sum of the gradient with respect to each time it appears. And that's what that equation says. So on the right, the notation with the vertical line and the I is saying the derivative of the loss with respect to WH when it appears on the ith step. Okay, so why is that true? To sketch why this is true, I'm going to remind you of the multivariable chain rule. So this is a screenshot from a Khan Academy article on the multivariable chain rule, and I advise you to check it out if you want to learn more, because it's very easy to understand. And what it says is, given a function f, which depends on x and y, which are both themselves functions of some variable t, then if you want to get the derivative of f with respect to t, then you need to do the chain rule across x and y separately and then add them up. So that's the multivariable chain rule. And if we apply this to our scenario, with trying to take the derivative of the loss jt with respect to our weight matrix wh, then you could view it as this kind of diagram, where wh has a relationship with all of these individual appearances of wh, but it's a simple relationship, it's just equality, and then each of those appearances of wh affect the loss in different ways. So then if we apply the multivariable chain rule, then it says that the derivative of the loss with respect to wh is the sum of those chain rule things, but the expression on the right is just 1 because it's an equality relation, and then that gives us the equation that I wrote on the previous slide. So this is a proof sketch for why the derivative of the loss with respect to our recurrent matrix is the sum of the derivatives each time it appears. Okay, so suppose you believe me on that. That is how you compute the gradient with respect to the recurrent weight. So a remaining question is, well, how do we actually calculate this in practice? So the answer is that you're going to calculate this sum by doing backprop backwards, kind of right to left, through the RNN, and you're going to accumulate this sum as you go. So the important thing is you shouldn't compute each of those things separately. You should compute them by accumulating. Like each one can be computed in terms of the previous one. So this algorithm of computing each of these gradients with respect to the previous one is called backpropagation through time. And I always think that this sounds way more sci-fi than it is. It sounds like it's time travel or something, but it's actually pretty simple. It's just the name you give to applying the backprop algorithm to a recurrent neural network. Any questions at this point? Yep.
So it seems that how you break up the batches matter your end result, like have a huge impact, because like you only update the next batch after you back to the time of the first batch. So if you break into much more granular batches, you'll get more fine results.
Okay, so the question is, surely how you decide to break up your batches affects how you learn, right? Because if you choose one set of data to be your batch, right, then you'll make your update based on that, and then you only update the next one based on where you got from there. So if you decided to put different data in the batch, then you would have made a different step. So that's true, and that is why stochastic gradient descent is only an approximation of true gradient descent. Because the gradient that you compute with respect to one batch is just an approximation of the true gradient with respect to the loss over the whole corpus. So yes, it's true that it's an approximation, and how you choose to batch up your data can matter, and that's why, for example, shuffling your data is a good idea, and shuffling it differently each epoch is a good idea. But the core idea of SGD is that it should be a good enough approximation that over many steps you will minimize your loss. Any other questions? Yep.
So as you're walking through the input, are you doing a back propagation step at each time step? So at step 1, you go back 1. At step 2, you do 2 steps backward. Step 1, you walk 2 steps backward, or so on.
So is the question, as you compute forward prop, do you start computing back prop before you've even got to the loss? Is that the question?
Yes.
I don't think so, right? Because you need to know what the loss is in order to compute the derivative of the loss with respect to something. So I think you need to get to the end. So if we assume for simplicity that there is only one loss which you get at the end of several steps, then you need to get to the end and compute the loss before you can compute the
something happened. I think the stream got disconnected and reconnected. But before we get into this, let's take a break, I would say, for a few minutes, and we'll get started with generating text with RNN. language model will be back in a couple of minutes. Okay, welcome back. Uh, let's get right into it. We'll be starting with generating text with an RNN model.
Generate text. You can also use it. So, okay, I'm going to move on for now. So that was a maths heavy bit, but now we're getting on to text generation, which someone asked about earlier. So just as we use the n-gram language model to generate text, you can also use an RNN language model to generate text via the same repeated sampling technique. So here's a picture of how that would work. You start off with your initial hidden state h0, which we have either as a parameter of the model or we initialize it to 0 or something like that. So let's suppose that we have the first word my, and let's suppose I supply that to the model. So then using the input and the initial hidden state, we can get our first hidden state h1. And then from there, we can compute the probability distribution y hat 1 of what's coming next. And then we can use that distribution to sample some word. So let's suppose that we sample the word favorite. So the idea is that we use the outputted word as the input on the next step. So we feed favorite into the second step of the RNN, we get a new hidden state, and again we get a new probability distribution, and from that we can sample a new word. So we can just continue doing this process again and again, and in this way we can generate some text. So here we've generated the text, my favorite season is spring, and we can keep going for as long as we like. Okay, so let's have some fun with this. You can generate text using an RNN language model. If you train the RNN language model on any kind of text, then you can use it to generate text in that style. And in fact, this has become a whole kind of genre of internet humor that you might have seen. So for example, here is an RNN language model trained on Obama speeches, and I found this in a blog post online. So here's the text that the RNN language model generated. The United States will step up to the cost of new challenges of the American people that will share the fact that we created the problem. They were attacked, and so that they have to say that all the task of the final days of war, that I will not be able to get this done. Okay, so if we look at this, and especially think about what did that text look like that we got from the n-gram language model, the one about the price of gold, I'd say that this is kind of recognizably better than that. It seems more fluent overall. I'd say it has more of a sustained context in that it kind of makes sense for longer stretches at a time. And I'd say it does sound tonally like Obama as well. So all of that's pretty good, but you can see that it's still pretty incoherent overall. Like, it was quite difficult to read it because it didn't really make sense, right? So I had to read the words carefully. So yeah, I think this shows some of the progress you can get from using RNNs to generate text, but still very far from human level. Here are some more examples. Here's an RNN language model that was trained on the Harry Potter books, and here's what it said. Sorry, Harry shouted, panicking. I'll leave those brooms in London, are they? No idea, said nearly headless Nick, casting low close by Cedric, carrying the last bit of treacle charms from Harry's shoulder, and to answer him, the common room perched upon it. 4 arms held a shining knob from when the spider hadn't felt it seemed. He reached the teams too. So again, I'd say that this is fairly fluent. It sounds tonally like the Harry Potter books. In fact, I'm pretty impressed by how much it does sound like in the voice of the Harry Potter books. You've even got some character attributes. I'd say that Harry, the character, does often panic in the book, so that seems right. But some bad things are that we have, for example, a pretty long run-on sentence in the second paragraph that's hard to read. You have some nonsensical things that really make no sense, like, I don't know what a treacle charm is. It sounds delicious, but I don't think it's real. And overall, it's just pretty nonsensical. Here's another example. Here is an RNN language model that was trained on recipes. So this one's pretty bizarre. The title is Chocolate Ranch Barbecue. It contains Parmesan cheese, coconut milk, eggs, and the recipe says, place each pasta over layers of lumps, shape mixture into the moderate oven and simmer until firm. Serve hot in bodied fresh mustard, orange, and cheese. Combine the cheese and salt together, the dough, in a large skillet, add the ingredients, and stir in the chocolate and pepper. So one thing that I think is even more clear here in the recipes example than the prose example is the inability to remember what's happening overall, right? Because a recipe, you could say, is pretty challenging because you need to remember the title of what you're trying to make, which in this case is chocolate ranch barbecue, and you need to actually, make that thing by the end, you also need to remember what were the ingredients at the beginning and did you use them. And in a recipe, if you make something and put it in the oven, you need to take it out later, and stuff like that, right? So clearly, it's not really remembering what's happening overall or what it's trying to do. It seems to be just generating kind of generic recipe sentences and putting them in a random order. But again, we can see that it's fairly fluent, it's grammatically right, it kind of sounds like a recipe, but the problem is that it's just nonsensical. Like, for example, shape mixture into the moderate oven is grammatical, but it doesn't make any sense. Okay, last example. So here's an RNN language model that's trained on paint color names. And this is an example of a character level language model because it's predicting what character comes next, not what word comes next. And this is why it's able to come up with new words. Another thing to note is that this language model was trained to be conditioned on some kind of input. So here the input is the color itself, I think represented by the 3 numbers, that's probably RGB numbers, and it generated some names for the colors. And I think these are pretty funny. My favorite one is Stanky Bean, which is in the bottom right. So it's pretty creative, and I think these do sound kind of like paint colors, but often they're quite bizarre. Light of Blast is pretty good too. So you're going to learn more about character level language models in a future lecture, and you're also going to learn more about how to condition a language model based on some kind of input, such as the color code. So these are pretty funny, but I do want to say a warning. You'll find a lot of these kinds of articles online, often with headlines like, "We forced a bot to watch 1,000 hours of sci-fi movies and it wrote a script," something like that. So my advice is that you have to take these with a big pinch of salt, because often the examples that people put online were hand-selected by humans to be the funniest examples. Like, I think all of the examples I've shown today were definitely hand-selected by humans as the funniest examples that the RNN came up with. And in some cases, they might even have been edited by a human. So yeah, you do need to be a little bit skeptical when you look at these examples. Yep.
In the Harry Potter one, there was like opening quote, and then there was a closing quote. So like, do you expect the RNN, like when it puts the opening quote and it keeps putting more words, do you expect the probability of the closing quote to like increase as you're going or decrease?
That's a great question. So the question was, we noticed that in the Harry Potter example, there were some open quotes and some closed quotes, and it looks like the model didn't screw up, right? All of these open quotes and closed quotes are in the correct places. So the question is, do we expect the model to put a higher probability on closing the quote, given that it's inside a quote passage? So I should say definitely yes, and that's mostly the explanation for why this worked. There's been some really interesting work in trying to look inside the hidden states of language models to see whether it's tracking things like, are we inside an open quote or a closed quote? And there has been some limited evidence to show that maybe there are certain neuron or neurons inside the hidden state which are tracking things like, are we currently inside a quote or not? Yep.
So like, do you think probability would like increase as you go more to the right? Like,
okay.
Increase?
So the question is, as the quoted passage goes on for longer, do you think the priority or the probability of outputting a closed quote should increase? I don't know. Maybe. That would be good, I suppose, because you don't want an infinite quote. But I wouldn't be surprised if that didn't happen. Like, I wouldn't be surprised if maybe some other worse trained language models just open quotes and never close them. Any other questions? Yep.
What are the dimensions of the W?
Okay, so the question is, what are the dimensions of the W matrices? So we're going back to the RNN stuff. Okay, are you asking about WH or WE or something else?
Yeah.
So WH will be, if we say that the hidden size has size n, then WH will be n by n. And if we suppose that the embeddings have size d, then WE will be d by n. N by d, maybe. Does that answer your question? Any other questions about generation or anything else? Yep.
So you said that there was a long sentence in the Harry Potter generated text.
Yep.
Is it ever sort of practical to combine RNNs with like a list of handwritten rules?
Sorry, is it ever practical to combine?
RNNs with a list of handwritten rules depending on the outcome.
Yeah, that's a great question. So the question was, is it ever practical to combine RNNs with a list of handwritten rules? For example, don't let your sentence be longer than this many words. So yeah, I'd say it probably is practical, maybe especially if you're interested in making sure that certain bad things don't happen. You might apply some hacky rules like forcing it to end early. I mean, okay, so there's this thing called beam search, which we're going to learn about in a later lecture, which essentially doesn't just choose one word in each step and continue. It explores many different options for what you could generate, and you can apply some kinds of rules on that, where if you have lots of different things to choose from, then you can maybe get rid of some options if you don't like them because they break some of your rules. But it can be difficult to do. Any other questions? Okay. So we've talked about generating from language models. So unfortunately, you can't just use generation as your evaluation metric for language models. You do need some kind of measurable metric. So the standard evaluation metric for language models is called perplexity. And perplexity is defined as the inverse probability of the corpus according to the language model. So if you look at it, you can see that that's what this formula is saying. It's saying that for every word xt, lowercase t, in the corpus, we're computing the probability of that word given everything that came so far, but it's inverse, so it's 1 over that. And then lastly, we're normalizing this big product by the number of words, which is capital T. And the reason why we're doing that is because if we didn't do that, then perplexity would just get smaller and smaller as your corpus got bigger. So we need to normalize by that factor. So you can actually show that this perplexity is equal to the exponential of the cross-entropy loss j theta. So if you remember, cross-entropy loss j theta is the training objective that we're using to train the language model. And by rearranging things a little bit, you can see that perplexity is actually the exponential of the cross-entropy. And this is a good thing, because if we're training the language model to minimize the cross-entropy loss, then you are training it to optimize the perplexity as well. So you should remember that the lower perplexity is better because perplexity is the inverse probability of the corpus. So if you want your language model to assign high probability to the corpus, right, then that means you want to get low perplexity. Any questions? Okay. So RNNs have been pretty successful in recent years in improving perplexity. So this is a results table from a recent Facebook research paper about RNN language models. And you don't have to understand all of the details of this table, but what it's telling you is that on the top row we have an n-gram language model, and then in the subsequent rows we have some increasingly complex and large RNNs. And you can see that the perplexity numbers are decreasing, because lower is better. So RNNs have been really great for making more effective language models in the last few years. Okay, so to zoom out a little bit, you might be thinking, why should I care about language modeling? Why is it important? I'd say there are two main reasons why language modeling is important. So the first one is that language modeling is a benchmark task that helps us measure our progress on understanding language. So you could view language modeling as a pretty general language understanding task, right? Because predicting what word comes next, given any kind of generic text, that's quite a difficult and general problem. And in order to be good at language modeling, you have to understand a lot of things, right? You have to understand grammar, you have to understand syntax, and you have to understand logic and reasoning, and you have to understand something about real-world knowledge. You have to understand a lot of things in order to be able to do language modeling properly. So the reason why we care about it as a benchmark task is because if you're able to build a model which is a better language model than the ones that came before it, then you must have made some kind of progress on at least some of those subcomponents of natural language understanding. So another more tangible reason why you might care about language modeling is that it's a subcomponent of many NLP tasks, especially those which involve generating text or estimating the probability of text. So here's a bunch of examples. One is predictive typing. That's the example that we showed at the beginning of the lecture with typing on your phone or searching on Google. This is also very useful for people who have movement disabilities because there are these systems that help people communicate using fewer movements. Another example is speech recognition. So in speech recognition, you have some kind of audio recording of a person saying something, and often it's kind of noisy and hard to make out what they're saying, and you need to figure out what words did they say. So this is an example where you have to estimate the probability of different options of what it is they could have said. And in the same way, handwriting recognition is an example where there's a lot of noise, and you have to figure out what the person intended to say. Spelling and grammar correction is yet another example where it's all about trying to figure out what someone meant, and that means you have to understand how likely it is that they were saying different things. An interesting application is authorship identification. So suppose that you have a piece of text and you're trying to figure out who likely wrote it, and maybe you have several different authors and you have text written by those different authors. So you could, for example, train a separate language model on each of the different authors' texts, and then, because you remember a language model can tell you the probability of a given piece of text, then you could ask all the different language models how likely the text under question is. And then if a certain author's language model says that it's likely, then that means that text, the text under question, is more likely to be written by that author. Other examples include machine translation. This is a huge application of language models because it's all about generating text. Similarly, summarization is a task where you need to generate some text given some input text. Dialogue as well. Not all dialogue agents necessarily are RNN language models, but you can build a dialogue agent that generates the text using an RNN language model. And there are more examples as well. Any questions on this? Yep.
So I know that for written text, we have developed ways back to embed them so that like a neural net could process it. But if we're doing handwriting recognition or speech recognition, there are other input sources such as images or audio files. How are we embedding those? And how do those work in conjunction with RNNs and word process?
Great question. So the question was, for some of these examples, such as speech recognition or maybe image captioning, the input is audio or image or something that is not text, right? So you can't represent it in the way that we've talked about so far. So in those examples, you will have some way of representing the input, some way of encoding the audio or the image or whatever. The reason I brought it up now in terms of language models is that that's the input, but you use the language model to get the output, right? So the language model generates the output in the way that we saw earlier. But we're going to learn more about those conditional language models later. Anyone else? Okay. So here's a recap. If I've lost you somewhere in this lecture, or you got tired, now is a great time to jump back in because things are going to get a little bit more accessible. Okay, so here's a recap of what we've done today. A language model is a system that predicts the next word. And a recurrent neural network is a new family, new to us, a family of neural networks that takes sequential input of any length, and it applies the same weights on every step. And it can optionally produce some kind of output on each step, or some of the steps, or none of the steps. So don't be confused. A recurrent neural network is not the same thing as a language model. We've seen today that an RNN is a great way to build a language model, but actually it turns out that you can use RNNs for a lot of other different things that are not language modeling. So here's a few examples of that. You can use an RNN to do a tagging task. So some examples of tagging tasks are part-of-speech tagging and named entity recognition. So pictured here is part-of-speech tagging. And this is the task where you have some kind of input text, such as the startled cat knocked over the vase, and your job is to label or tag each word with its parts of speech. So for example, cat is a noun and knocked is a verb. So you can use an RNN to do this task in the way that we've pictured, which is that you feed the text into the RNN, and then on each step of the RNN, you have an output, probably a distribution over what tag you think it is, and then you can tag it in that way. And then also for named entity recognition, that's all about tagging each of the words with what named entity type they are, so you do it in the same way. Okay, here's another thing you can use RNNs for. You can use them for sentence classification. So sentence classification is just a general term to mean any kind of task where you want to take a sentence or other piece of text and then you want to classify it into one of several classes. So an example of that is sentiment classification. Sentiment classification is when you have some kind of input text, such as, let's say, overall, I enjoyed the movie a lot, and then you're trying to classify that as being positive or negative or neutral sentiment. So in this example, this is positive sentiment. So one way you might use an RNN to tackle this task is you might encode the text using the RNN, and then really what you want is some kind of sentence encoding so that you can output your label for the sentence, right? And it would be useful if you'd have a single vector to represent the sentence rather than all of these separate vectors. So how would you do this? How would you get the sentence encoding from the RNN? One thing you could do is you could use the final hidden state as your sentence encoding. So the reason why you might think this is a good idea is because, for example, in the RNN, we regard the final hidden state as this is the thing you use to predict what's coming next, right? So we're assuming that the final hidden state contains information about all of the text that has come so far, right? So for that reason, you might suppose that this is a good sentence encoding, and we could use that to predict, what sentiment is this sentence. It turns out that usually a better way to do this, usually a more effective way, is to do something like maybe take an element-wise max or an element-wise mean of all these hidden states to get your sentence encoding. And this tends to work better than just using the final hidden state. There are some other more advanced things you can do as well. Okay, another thing that you can use RNNs for is as a general purpose encoder module. So here's an example that's question answering, but really this idea of RNNs as a general purpose encoder module is very common, and you use it in a lot of different deep learning architectures for NLP. So here's an example which is question answering. So let's suppose that the task is you've got some kind of context, which in this situation is the Wikipedia article on Beethoven, and then you have a question which is asking what nationality was Beethoven. And this is actually taken from the Squad challenge, which is the subject of the default final project. So if you choose to do the default final project, you're going to be building systems that solve this problem. So what you might do is you might use an RNN to process the question, what nationality was Beethoven? And then you might use those hidden states that you get from this RNN over the question as a representation of the question. And I'm being intentionally vague here about what might happen next, but the idea is that you have both the context and the question are going to be fed some way, and maybe you'll use an RNN on context as well. And you're going to have lots more neural architecture in order to get your answer, which is German. So the point here is that the RNN is acting as an encoder for the question. That is, the hidden states that you get from running the RNN over the question represent the question. So the encoder is part of a larger neural system, and it's the hidden states themselves that you're interested in because they contain the information. So you could have taken element-wise max or mean, like we showed in the previous slide, to get a single vector for the question, but often you don't do that. Often you'll do something else which uses the hidden states directly. So the general point here is that RNNs are quite powerful as a way to represent a sequence of text for further computation. Okay, last example. So going back to RNN language models again, they can be used to generate text, and there are lots of different applications for this. So for example, speech recognition. You will have your input, which is the audio, and as a student asked earlier, this will be represented in some way. And then maybe you'll do a neural encoding of that. And then you use your RNN language model to generate the output, which in this case is going to be a transcription of what the audio recording is saying. So you'll have some way of conditioning, and we're going to talk more about how this works in a later lecture, but you'll have some way of conditioning your RNN language model on the input. So you'll use that to generate your text. And in this case, the utterance might be something like, "What's the weather?" question mark. Yeah?
In speech recognition, we often look for error rate to evaluate, but if it's possible to still give the length.
Okay, so the question is, in speech recognition, we often use word error rate to evaluate, but would you use perplexity to evaluate? I don't actually know much about that. Do you know, Chris, what they use in speech recognition as an eval metric?
So, I mean, for vowel speech recognition, we have word error rate is standard, but should evaluate just the language model part. People use perplexity.
Right. The answer was you often use WR for eval, but you might also use perplexity. Yeah. Any other questions? Okay, so this is an example of a conditional language model. And it's called a conditional language model because we have the language model component, but crucially we're conditioning it on some kind of input. So unlike the fun examples like with the Harry Potter text, where we were just generating text basically unconditionally, you know, we trained it on the training data and then we just start it with some kind of random seed and then it generates unconditionally. This is called a conditional language model because there's some kind of input that we need to condition on. Machine translation is an example also of a conditional language model, and we're going to see that in much more detail in the lecture next week on machine translation. Are there any more questions? We have a bit of extra time, I think. Yep.
I have a question about RNNs in general.
Do people ever combine the RNN pattern/architecture with other neural networks? Say you have, n previous layers that could be doing anything, and at the end of your network, you want to run them through 5 recurrent layers. Do people mix and match like that, or are these sort of specialized so they really only use this by themselves?
The question is, do you ever combine RNNs with other types of architectures? So I think the answer is yes. You might, have other types of architectures to produce the vectors that are going to be the input to your RNN, or you might use the output of your RNN and feed that into a different type of neural network. So yes. Any other questions? Okay. So before we finish, I have a note on terminology. When you're reading papers, you might find often this phrase vanilla RNN. And when you see the phrase vanilla RNN, that usually means the RNNs that are described in this lecture. So the reason why those are called vanilla RNNs is because there are actually other more complex kinds of RNN flavors. So for example, there's GRU and LSTM, and we're going to learn about both of those next week. And another thing we're going to learn about next week is that you can actually get multi-layer RNNs, which is when you stack multiple RNNs on top of each other. So you're going to learn about those, but we hope that by the time you reach the end of this course, you're going to be able to read a research paper and see a phrase like stacked bidirectional LSTM with residual connections and self-attention, and you'll know exactly what that is. That's just an RNN with all of the toppings. All right, thank you. That's it for today. Next time... Next time we're learning about problems and fancy RNNs.
Okay, I think one of the great things was there was a good recap, so a good idea to just round everything up. Yeah, I mean, I've heard about RNNs, also tried to read about those, but never really got a good understanding. So thanks to today's lecture, at least I have some context of what's going on inside an RNN architecture. But yeah, I mean, LSTM, GRUs, all of these attention, this is all what I want to learn. So the more I get to watch these videos, the more I get excited about what's coming next. And obviously that last slide about terminologies with the explanation was fantastic, because I think terminology is a very important factor for you to feel that you know stuff, because when you get an idea of what it actually is trying to say, you know what to even search or what to even look for. Without even having an idea of terminology, you're just completely lost. But overall, yep, great lecture, and Abby was a great she was great at explaining stuff as well and answering all of those questions. I think this lecture also had a lot of questions, and so there was a good back and forth. But apart from that, I think that's it for today. subscribe to the channel, hit that bell icon so that you're aware of when I'm streaming. As I said, I'm trying to keep this super disciplined, so I'm streaming 6:30 Central Time. I'm based out of Chicago, so 6:30 a.m. Central Time every day. That's my plan, but we'll let you know if that changes. Reach out to me on social media. I have everything linked in the description. The course materials are also linked down below if you want to read through the slides again. I have the original lecture series, the playlist on YouTube also linked. All you need to do is just scroll down below and you'll find everything. I have all of those information properly tagged as well. But with that, I will take my leave. That's it for today. I will see you guys tomorrow. Thank you.